Feel free to ask me any questions. We got about 4 minutes, but I'm just getting my notes ready and all that sort of stuff. So uh, feel free to ask me questions if you have them. You can go ahead and text your or chat your first and last name as well. And today is the 18th. I seem to have the notes ready now. Where is it? Ah, I bumped my head. I was like, which one of those people didn't put their name up? And then I realized it was my name that was missing. We got a couple minutes. I'll be right back, everybody. I'm doing something up here. You need some? Yeah. Well, that's a big cake. All right, got about 1 minute left. Feel free to ask me questions. Like I said, we'll get started in a few. All right, I guess that's good enough. So I want to start off with talking about chapter 3. Last time we went over a pretty extensive addition of velocity, addition of vectors problem. And specifically, I had 4 vectors. I stated their magnitude and direction in 4 different ways. So you'd have some familiarity with the common ways in which we can specify vectors. And then I showed you how to break them down into components. And then we added the like components to get the X component of the resultant vector. And the resultant is the name that we gave the vector that stands for the sum of vectors. So, you know, if vectors are A and B are added, the sum of that's called the resultant, but that's also called the resultant when vectors A, B, C, and D are added. We also talked about multiplying scalars by vectors. So we saw, for instance, that if you had a vector and you multiplied it by 2, it became a vector that was twice as long, but in the same direction. If you multiplied it by a number less than 1, then it became a vector that was shorter. So for instance, if we multiplied it by 1/2, then it would be half the length of the vector. We also realized that when you multiply it by a negative number, it does the same thing as when you multiply by a positive number, except now it also takes the head and flips it 180 degrees. So you can actually implement that by changing the direction to the direction it had plus 180 degrees. Or sometimes it's more convenient to do the direction you had minus 180. So for instance, if you're at like 240 degrees, If you add 180 to it, that becomes a really unreasonably large number and doesn't make much sense. But if you do 240 minus 180, you're still in that realm. So it's kind of nice. I wanted to say specifically, we'll learn more about dot products, which is also called a scalar product, which is also called an inner product. And with those dot products, uh, there's a very specific way of doing it. We'll learn about that. And actually, I use that to teach you guys how better to understand the law of cosines, which I found very difficult to do until I discovered this way of deriving it. And then it made much more sense to me and was easier to apply. We'll do the cross product, which is also called the vector product, which is also called the vector product. And that one's actually related to what we call in differential forms and differential geometry, we call a wedge product. And you can even do a combination of the two. If, for instance, if you take A and B and take their cross product, you'll get a vector C that's perpendicular to A, but the vector C's magnitude will be equal to the area of the parallelogram created by A and B. So if you then dot that vector with a third vector, let's call it D, then you'll get the volume of a parallel pipette whose cross-sectional area is the parallelogram made by AB, and then whose volume is ultimately made with the addition of the vector D. Okay, so there's a lot of neat stuff that comes from there. I also wanted to let you know that if you ever just need to make a vector, for instance, if you want a vector that points from the origin to some point in space, let's say the point is parenthesis x comma y close parenthesis, so it's in 2 dimensions. It could also be parenthesis x comma y comma z close parenthesis for 3 dimensions. But if you wanted a vector that just started at the origin and ended on that point, then you could just take x from the point and call that the x component. So you take the x and put it in front of I hat. You take the y and put it in front of j hat. And you take the k or the z if you had it and put it in front of k hat. And then you would put plus signs between all of them. And then you'd have a vector that points from the origin to the point x, y, z. Or more generally, if you had a vector that you wanted to go from one point, call it comma x1, or excuse me, parenthesis x1 comma y1 close parenthesis, and you want it to extend up to parenthesis x2 comma y2 close parenthesis, then you could just do subtraction of the final point minus the initial point. So you do x2 minus x1, that would be the x component, and you'd put it in front of I hat, and you do y2 minus y1, that would be the y component, you put it in front of j hat. And if you had a z, you'd say z2 minus z1 and put that in front of k hat and then put plus signs between them. And that would be the vector pointing from x1, y1, z1 to x2, y2, z2. Now, one of the things we do often want to do is we would like a vector that's parallel to a particular line. For instance, the line I just mentioned was the line that happens to go through x1, y1 and x2, y2. If you wanted a vector that was along that line or parallel to that line, but you wanted to have a very specific magnitude, what you could do is make that vector by doing x2 minus x1, y2 minus y1, z2 minus z1, and then find the magnitude of that vector by the Pythagorean theorem, assuming you're in rectangular coordinate systems. Once you found that magnitude, if you then multiplied the vector by 1 over that magnitude, in other words, it's like you're dividing by the magnitude, then you'd make that new vector into a unit vector. At that point, all you have to do is multiply it by any number you want, and that'll actually make a vector that has the magnitude you desire and points in the direction you desire. Okay? One other thing, hopefully this is obvious, but it might not be because I didn't really stress it or point it out, but when we multiplied, for instance, when I multiplied 2 times a vector, what would actually happen on that in terms of components is the 2 would be multiplied by the x component. So the x component would go from a sub x to 2a sub x. The y component would go from a sub y to 2a sub y. And the z component would go from a sub z to 2a sub z. Same thing if it was a negative number, it would just become, of course, the negative times, 1az or 2az or whatever. So just to keep that in mind, that's what happens when you multiply by a vector, or by a scalar, it actually multiplies by each of the terms, or excuse me, by each of the components. Okay, so you can sort of think of it as like a distributive property. So you have an AX I hat, AY J hat plus AZ K hat. And if you multiply by two, then that two is going to be distributed to each of the three components. And that's the way you should think about it. Now that I have that, I think I want to just go ahead and jump into projectile motion. I'll just let you know that as the semester goes in 241, you'll learn more and more vector stuff, vector algebra. Not as much vector calculus, but once you get into 242, there will be some vector calculus that you'll learn, and you'll learn it later on in other classes. So feel free to contact me at any time if you need any help. I've had a lot of experience in learning this process. Uh, there's a lot of math I don't know yet. There's a lot of math I have some hints about. Like, for instance, I have a fairly decent knowledge of group theory and statistics and some stuff like that. But a lot of maths I don't know that much about. I do have some knowledge of differential geometry, tensor calculus, calculus on manifolds, differential equations, partial differential equations. But there's a whole lot of math in the world that I just don't know. Okay. But I'm always here for you guys, so always email me and put something to catch my attention in the subject line. That way you'll get me. You normally have to put your PHY 242 night or something like that in your subject line when you're in my class. If you're not in my class, just put something to catch my attention and I'll probably see it. Okay. So let's get started with the projectile motion problem. In studying projectile motion, what I want you to understand is just about every physics textbook I've ever run into for algebra-based, which some people call trig-based, but algebra/trig-based physics, or for calculus-based physics, they all have this one photo. And the photo is almost always a red ball and a yellow ball next to each other. And what it is I think they actually had like the aperture open in a dark room, or like a completely black room, and then they had a strobe light going, and that strobe light might blink every 10th of a second, or every 20th of a second, or maybe even every 100th of a second. I'm not sure. But the main thing is, at one point, those two balls, one of them is shot perfectly horizontally, and at the exact same instant, the other ball is dropped. So let's say this ball is shot. So it's shot horizontally like this. But of course, it's on planet Earth, so it's not going to just shoot out horizontally, it's going to fall. But here's the neat thing. When you shoot out that ball horizontally and the other ball falls at the same time vertically, what you discover is after, let's say, 0.02 seconds or something like that, 0.02 seconds, then they're both at the same height. And then after 0.04 seconds, they're both at the same height. And after 0.06 seconds, they're both at the same height. And what's going on is that horizontally shot ball is falling the exact same rate vertically as the dropped ball. And what you're supposed to glean from that is the idea that the vertical acceleration does absolutely nothing to the horizontal motion. And in fact, the horizontal motion is independent of the vertical acceleration. Okay. So now that you have that in mind, I'll tell you the big thing that I do when I'm actually solving projectile motion problems is I imagine it's two problems. So what you have is a velocity where a projectile is fired at some angle above the horizon. That's got to be broken up into an X component and a Y component. And the two motions that I'm talking about is one object's been thrown up with no air resistance, and it's in what we call free fall, but it's been thrown up with the vertical velocity that's equal to the Y component of the initial velocity. And it just goes straight up, reaches some max height, and falls straight back down. At the same time, there is sort of like a car rolling, or a ball rolling or something like that, horizontally with a constant speed. That constant speed happens to be the X component of velocity. So you treat those two types of motion completely separately, but you act like time is the one thing they have in common, so that, for instance, how fast you throw it up gives you a certain amount of time that it's allowed to be in the air. If you figure out how long it's actually allowed to be in the air, then all you have to do is take that time and multiply it by that constant horizontal velocity, and that will actually give you what we call the range, how far it went downfield. Okay, so that's the big trick to solving projectile motion problems. I'm going to treat it as if we're wanting to ask the simplest, easiest, straightforward questions, which are things like, what's the max height my projectile will reach? And I'm going to go on the assumption that we're launching it and it's landing at exactly the same height. A lot of symmetry happens when we use that setup. And that's not the way all problems are done, but you're at a good point where you can jump off and do those other problems once you've seen two ways that I'm getting ready to show you now. But the main thing is, like I said, you might say, well, what's the max height? Well, the max height can be solved by first figuring out at what time, say, the vertical velocity becomes zero. In other words, if the vertical component of velocity were, let's say, 30 meters per second, then it's going to get a little bit more than 3 seconds that it's allowed to climb before its velocity reaches zero. At the end of that 3 and some change seconds, the vertical velocity is zero. And it's actually, since the vertical velocity is zero, that means the vertical velocity was previously upward and will immediately be thereafter downward. So it's actually at its max height. So once you figured out that time, then you just go back and plug it into the equation for the height as a function of time, and that'll give you the height max. If you then say, well, at what time will the y height be zero? You can take your equation for the y motion, set that equal to zero, and you're going to get one result that's t equals zero for obvious reasons, because obviously you shot the projectile at t equals zero from the ground height. But the other time will be the actual time that I'd call the hang time. It's the time that it's aloft. So you could call it the hang time or T sub H or T sub A or something like that. Once you have that time, you just multiply it by, again, that horizontal velocity that's not changing, and that'll tell you how far it went afield. Other questions are, of course, how long is it in the air? What's the velocity just before it hits the ground, all that sort of stuff. So we're going to tackle all that. So let's get started. I'm going to start by sharing my screen. Feel free to ask me questions you might have at any time, including now. So let me go ahead and share my screen, but feel free to start asking questions now if you'd like. Okay. So you're now looking at our at my iPad, and I'm going to draw a coordinate system to start studying the projectile motion. And I'm going to do it with some very specific data, and I'm going to use a special triangle because the special triangle makes my life a lot easier. I don't have to do any calculation and stuff like that. So what I'm going to do is I'm first going to imagine a vertical axis, and then I'm going to imagine a horizontal axis. Okay. That wasn't really the place that I had planned it, but I accidentally hit my hand, so that's good enough. Okay, so now we have that, and this is going to be what I call my X direction, and this is going to be what I call my Y direction, and that X direction didn't turn out so nicely, so I'm going to draw that because, again, my hand got I bumped into it something and caused a problem. So what we're going to imagine is that there was an initial velocity vector V0 is equal to 50.0 meters per second, and it was fired at 36.87 degrees above the horizontal. And I'm going to assume the ground between here and where it lands is exactly level. I'm also going to assume that air resistance is negligible. And of course, you should think about all the ways that air resistance isn't negligible. You can watch some football and see some really crappy quarterbacks. I would advise you that you might want to look at the history of the Washington Commanders. because they're my team, and we've had just well, we've had a couple decades of problems. I'll say that. So even when we won the last Super Bowl, it was under Rippon, and he was notorious for throwing duck balls. But that's what happens when you get bad air resistance. Is the projectile, instead of arching like it's supposed to, it just sort of goes like this and then falls out of the air, and hopefully somebody catches it. Anyways, so what we're going to do is we're going to imagine that this projectile is fired at 50 meters per second at 36.87 degrees above the horizontal, and that it's going to trace out, of course, a parabola. During that process, it's going to reach a height that I'll call H max, and that's one of the things I'd like to figure out. I'm going to say that occurs at a time t 1/2, which is also something we might want to know. I'm also going to say that the instant before it hits the ground, it has a final velocity, v final, and that's something we want to know. Okay. I'm also going to say that it lands a certain distance downfield, and I'm call that distance the range, and I'll give it the symbol R. And I'm going to say that happens at a time t, which I'll call HT for hang time. If you pay attention to football, you'll know hang time is an important number for punters. Not that I want to say punters are the know all and end all. They're obviously the weak little wishes of the, the football world, but they are very skilled, and kickers and stuff like that definitely need to know how to kick, and they usually have a very good background in soccer or something. But the main thing is, when we kick a punt, our ideal goal is to keep it in the air for very long. And if we're deep in our own territory, we'd ideally want to kick it as far away as possible. But if you're in like the 40, 45-yard line, it'd be really ideal to make it land roughly around the 1-yard line so one of your players can down it, and they'd have a real difficult thing. But by giving it a long hang time, your defensive players can more or less form a circle around the catcher before he catches the ball. So that's why we do that. So these are the problems I'm going to be thinking of. Now, of course, problems that you work, like the ones at the end of the chapter and the ones in the homework, can be a little more complicated. They might ask you, instead of me giving you the initial velocity and the initial angle, they might ask you for the initial velocity for it to go a certain distance, or they might ask you what angle it has to be fired so that it can clear the front of a cliff and then land on top of the cliff. I think I can give you enough with the examples that I do here. I think I can give you enough experience so that you'll have some idea of how to attack those problems as well. So we're going to do it in this case in terms of this particular problem. And then I'm going to do it in a very symbolic way with just graphical, or excuse me, with just algebraic symbols. And we'll get robust answers that work on all problems, as long as you're launching and landing at the exact same height, where a lot of symmetry comes in. Okay. So we know we have certain issues. Like, for instance, I can tell you, since we're ignoring air resistance, that implies A, the acceleration, is negative G J hat. Okay. And I just put the negative there because we obviously drew up as the positive Y direction. And since it's the Y direction, the J hat is the appropriate direction for the gravitational acceleration. And it's important for you to understand that the instant this ball leaves the barrel of the gun, since we're ignoring air resistance, the acceleration is going to be negative G the whole time. A lot of people think there's only acceleration like just as it hits the ground, and or maybe just at the top, or weird stuff like that. No, this thing's accelerating the whole way. Okay. The same thing when you throw a ball straight up in the air. As soon as it leaves your hand, the acceleration is 9.8 meters per second every second downward. And it's going to stay that all the way up. When it comes to a stop, it's still accelerating at negative 9.8 meters per second. And then on the way down, it's still accelerating at negative 9.8 meters per second every second. So let's keep that in mind just from a conceptual standpoint to know, the facts of physics. So our kinematic equations, of course, I've derived those. You have some explanation of what they are. It turns out that you can pretty much do everything you need with just one of them. I'll show you ways where you can use the other ones, but really there's just one that you need. So what I'm going to do is I'm first off going to tell you that y, which you can also call y as a function of t, is going to give me the y coordinate of the ball at any point of the projectile, I should say, at any point in time. And because I know the acceleration is negative g, it's going to be negative, it's going to be negative 4.90 meters per second every second times t squared plus v0 y times t, and then plus y0. Now, I almost never use a y0, but the times that I do use initial coordinate, it's in the y direction. I've never used x0 being anything other than 0, but y0, I have occasionally done that. For instance, if you're firing off of a cliff onto the ground below, then you might want to say y0 is the initial height, and you'd put the origin down below at ground level. If you're firing it out of a hole, you might want to say that the origin is up above, and therefore the y0 is a negative number. That's acceptable, but I've never ever tried to use it with the x. Now, what we have to realize is with this particular vector that I've drawn, I have essentially 50.0 meters per second that way, 36.87 degrees there. And this right here is called V0. Oops, I didn't write that very clearly. Actually, I wrote all that crappy. Let me make it in a bigger area so you can actually see. So let's say it looks more like this. Okay. And this is 50.0 meters per second, which is what we call V0, the initial magnitude of the velocity. This angle is 36.87 degrees. This right here is V0 sub x, meaning the x component of the initial velocity. And this right here, notice they're supposed to all meet at the same point here. This is V0y, the y component of the initial velocity. Okay. Now, we happen to know of a very specific triangle. It's the 3, 4, 5 triangle. So I could do it like this and then this. Well, something like that. That's not the prettiest I've ever drawn. But this side is 3, this side is 4, this side is 5. This angle, since it's opposite the big side, is 53.13 degrees. It actually goes on. There's a lot of decimals there, but 53.13 is pretty. That's 4 sig figs for an angle. That's pretty high. And of course, this angle is 36.87. So that's the triangle I'm actually using here. And from that, remember, you can always go ahead and take the time and write out what the sine is, then take the time, write out what the cosine is. You're always able to do that. And I recommend you do that initially every time. Okay. After you feel really comfortable, like you've nailed this stuff, then you can just start writing the x component and the y component without writing out the full sine and cosine first. So let me write out the full sine first. So I'm going to say the sine of 36.87 degrees. I would normally say that's equal to, the x component over the magnitude, or the magnitude over the x component, or something like that. But this time I'm going to first say exactly what that is, because I know what the sine is from looking at the special triangle I have up above. So for instance, if I want to take the sine of 36.87, that's some old horse, or so some sine is opposite over hypotenuse. So the opposite is 3 and the hypotenuse is 5, and 3/5 is of course 0.6. Now, if I used all the decimal places of the angle, then this would be 0.6 to an infinite number of decimal places. But as it is right now, I'm using 4 decimal places, so I could really only justify 4 sig figs. Excuse me, I did one extra there. Okay, so that would be 4 sig figs. Now I'm going to say what it's equal to in terms of V0, V0y, V0x. I suspect all of you can tell me, and I want you to take the time to make your guess right now. Hopefully it's more than a guess. And then I'm going to write down the right answer, and hopefully you all will get it right. So remember, some old horse or so means sine equals opposite over hypotenuse. So I'm going to call this V0y over 50.0 meters per second, which is, of course, V0. Similarly, I'm going to write cosine 36.87 degrees. Now, from this one, remember cosine is ka, so that's cosine is adjacent over hypotenuse, or k Mahapan is cosine is adjacent over hypotenuse. 4 is the adjacent angle, and 5 is the hypotenuse. So this is going to be 4/5, which is 0.8000. Now I'm going to do it in terms of the V0s. So we can see the adjacent side to the 36.87. Obviously, one side touching the angle is in fact the hypotenuse, and the other one's the actual adjacent side. So the adjacent side is V0x, and the hypotenuse is the magnitude. So I'm going to write 50.0 meters per second. So what you can say is that V0x is equal to 50.0 meters per second times the cosine of 36.87 degrees. And of course, 36.87 is 4/5. So 4/5 times 50 gives you 40.0 meters per second. I carried one extra sig fig there, or one extra digit there. It's not a sig fig. V0y is 50.0 meters per second times the sine of 36.87 degrees. 36.87 is 0.6, which is 3/5. And of course, 3/5 times 50 gives me 30.0. Again, adding one extra digit that's not significant, meters per second. So now that I have that, I can make the y equals y of t a little more precise. Y equals y of t is equal to negative 4.90 meters per second every second times t squared plus 30.0 meters per second times time. And I'm saying y0 is going to be equal to 0. Okay. Now, I didn't like that my parenthesis ran into my 4 here, so I'm going to fix that real quick. Okay. So that's the y motion. So the equation we're using here, of course, is x equals 1/2 at squared plus v0t plus x0. Y'all are all familiar with that. That's the one we get when we integrate a equals dv dt, and a is a constant. We first get at, and then the integration constant turns out to be v0. And then we have v is equal to v0 plus at, and we set that equal to dx dt. We integrate that. That gives us 1/2 at squared plus v0t, and then the integration constant turns out to be x0. Okay, so that's where that came from. Now we can actually use the same equation for x, only x has an acceleration of 0, so it's a little simpler. It's actually a lot simpler. So x of t is just going to be the same thing, 1/2 at squared, where a is 0, plus v0t, where v0 is v0y, or excuse me, v0x, and then times t, and then plus x0, but x0 is going to be 0. So this is literally just going to be 40.0 meters per second times time. So that's the coordinate x at any point in time t from t equals 0 to t hang time. Obviously, once it bounces, all things are off. Okay. And we're assuming that it was fired at t equals 0. So that's why it has to be between 0 seconds and THT. Similarly, the y of t gives us the y coordinate at any point in time for t equals 0 on up to THT. Everybody get that? Now,
Professor, you said it's just because it crosses the x-axis one time. That's why it's just 40.
oh, okay. So with this case, remember the equation. Let me write it over here and I'll erase it in a second. But the equation we're using is 1/2 a, oh, excuse me, 1/2 a t squared plus v0 t plus x0. That's the kinematic equation we're using.
Right.
See that I put the projectile at the origin initially, so that's why that's 0. We don't have any acceleration in the x direction. As we saw, the acceleration is purely in the y direction. And I told you that red ball, yellow ball scenario, so you know that the y acceleration doesn't have any effect on the x motion. So because of that, we know that this quantity is 0. So all we're left is just the initial velocity, which in this case is purely in the x direction, times t.
Okay.
Does that make sense?
Yeah.
Okay. Now, believe it or not, you can do essentially everything here, but you don't have to, okay? For instance, if I wanted to solve for H max, so H max will be the first thing I'm going to solve for, and I'm going to solve it in black. So H max, oops, I'm going to use black as like my solution color. So H max, what I know about H max is a maxima of y of t. Does that make sense to everyone? If you look at the function of y of t, it makes a parabola like that, and the highest point on it is a maxima. So to find a maxima, we take the derivative and set it equal to 0. That'll give us the time at which the h max occurs, and then we go back and put it in the y, and that'll give us the height at the time it reaches the h max. Does that make sense? So dy dt equals 0 gives us, if I take the derivative of the y of t, which I will say is this equation right here, and I'm going to say this is equation 2 right here. If I take the derivative of that, the derivative of negative 4.9 t squared is negative 2 times 4.9 times t squared, or times t. And of course, that means negative 9.80 meters per second every second times t, plus I take the derivative of 30.00 meters per second times t. That just gives us the 30 meters per second. And then, of course, I've taken the derivative and I got to set that equal to 0. And that gives me specifically t1/2. So from that, I get t1/2. And of course, I called that t1/2 because it looks from symmetry, it looks like that would be exactly half the time. Okay. And in fact, the symmetry requires it to be half the time as long as it's launched and lands at the same height. So we can use that every time we're launching and landing from the same height. So now I can solve for t1/2, and that turns out to be, oops, that turns out to be 30.0 meters per second divided by 9.80 meters per second per second. Because notice the negative 9.8 t1/2 will go to the other side and become positive, and then I'll just divide both sides by 9.8, and that gives me 3.016 if I remember correctly. Let's check. So 30, or maybe it's 30 point, yeah, I think it's 3.016. So 30 divided by 9.8 is, oh, it's, yeah, I did have the 6 and 1 backwards. So it's going to be 3.0612. Obviously, I only have 3 sig figs. I normally carry 2 myself, so I'm going to underline the 1 and the 2. And notice that that answer is T1/2 equals 3.06. So that is one of our answers, by the way. I can write that right up here. Now, according to our method, I'm going to now plug that in y because H max is equal to y of T1/2. So I get that H max is equal to, now I'm plugging it in equation 1. So this is negative 4.90 meters per second times T1/2 is 3.0612 seconds squared plus 30.0 meters per second times 3.0612 seconds. And when you do that, you get negative 4.9 times, I'm going to click on shift answer, and then I'm going to square that, plus 30 times shift answer again, and that all looks correct, and that gives me 45.918 meters. Now notice when I did 4.90 times 3.061 squared, that essentially, I was multiplying two 3 sig fig numbers. So the answer came out to 3 sig figs, and that was like 45.9. So I'm good up to the first decimal place. So I just make a mark that this is significant up to first decimal. Oh, I should say decimal spelled with an S, not a C. And now I'll do 30 times 3.016, or excuse me, 3.061. And that gives me 91.8. So that's also good to one decimal place. So I do know that the first decimal place is in fact significant even after the addition part. So I can go ahead and underline the 1 and the 8 to show us that that's not significant. And this is equal to H max, which is another thing we wanted to solve for. Any questions on that? Gotcha. Now, there is another way. That way required us to solve for time. You don't always have to solve for time, but listen to this. Another way we could actually solve for H max is we realize that the projectile is going to start slowing down immediately upon leaving the barrel of the gun. Okay. And in actuality, it's just the y component that's going to be decreasing. I'll get you in a second, Dylan. So it's just the y component that's going to be decreasing because, as we said, x is going to be 40.0 meters per second times t. So that's never changing. But if we think about it that way, then we realize, oh, wait a second, at h max, the vertical component of velocity will be 0. So what we could do is find the vertical component of velocity and set that equal to 0. How would we find the vertical component of velocity when we just have y of t? Anybody? I'll get you in a second, Dylan.
using like sine and cosine of whatever angle to find it?
Yeah, we actually already did that part initially, finding the initial one, but I've got y as a function of t now. You're thinking right, but I'm wanting to do it at a later time. So what I want to know is, can I write v of t, where I specifically mean v sub y of t? Can I find the y component of velocity as a function of time? I do have the y position as a function of time. Anybody?
Could you differentiate it?
Exactly. Velocity is the derivative of position with respect to time. So if I took the derivative of y of t, then I would get v sub y of t. And then I would set that equal to 0 because I want to know at what time the velocity is 0. And then I could plug that back in. But that's exactly what we already did, isn't it? Remember, I took the derivative of y of t, just treating it like a regular function and finding the maxima. So the other way is exactly the same way, except we're using our knowledge of physics, which is that the velocity of in the y direction is the derivative of v with respect to t. So I'll just add that we now have v sub y of t is equal to what I actually got, which is negative 9.80 meters per second every second times t plus 30.0 meters per second. And I'm going to call that equation 3. Now, while we're at it, we can go ahead and say v sub x of t is equal to dx dt. And therefore, when I take the derivative of that, I'm just going to get 40.0 meters per second. And I'm going to call that equation 4. So there's another equation I could use. I want to reiterate that this was dy dt. Okay, so that's another way. Now let's try doing it away without sign. Can anybody think of a kinematic equation that can allow us to find the height without first finding the time?
Is that the one where it's like the final velocity squared
That's the one.
equals the initial velocity squared plus 2 times the acceleration in the distance?
Exactly. Good job. All right. Now, Dylan had a question. So go for it, Dylan. I think that was you that answered too, wasn't it?
No, I think that was Alec.
Oh, okay. Gotcha.
So at towards the beginning, my computer was messing up. I was wondering where you got formulas 1 and 2.
Okay. So 1 and 2 both came from the kinematic equation that I wrote down a second ago in black. It's x equals 1/2 at squared plus v0t plus x0. Remember us deriving that kinematic equation in chapter 2?
Mhm.
So that applies to any problem in which we have a constant acceleration, a equals a constant. So using, I'll write it again here, x equals 1/2 at squared plus v0t plus x0. When we apply that in the y direction, it becomes y equals negative 1/2 g, because that's the acceleration in the y direction, t squared plus v0y times t plus y0. When we apply that in the x direction, we get x is equal to, now the acceleration in the y direction is 0, so that first term disappears, and all we're left with is v0x times t plus x0. And we're free to choose x0 and y0 equal to 0, so that's how that got in. Does that make sense, Dylan?
Okay. Yeah.
Okay. So that's where that came from.
Okay. Cool.
And
Thanks.
I didn't take the time to write out all that stuff, but I just wanted to remind you that this H max is a maxima turned out to be exactly the same way as us concluding that H max occurs when the y component of velocity is equal to 0. Okay. The same math, everything. It just was a different way of interpreting it. So now I'm going to erase this. And now we're going to use that other method that, I forgot who the student that said it was. We're going to use V0 squared, or V squared is equal to V0 squared plus 2. In this case, it's negative G times Y minus Y0. But of course, Y0 is 0 because we already made it so. And A, of course, is negative G. And what we're going to do is we're going to say that V is 0. Okay. So now that I have that, I'm going to do another way. So let's say right here, alternative. V squared y is equal to V0 y squared minus 2G y is the version we just got. If we set Vy equal to 0, then y will equal H max. So H max is equal to negative V0 y squared over negative 2G. So we'll get negative 30.0 meters per second squared divided by negative 2 times 9.80 meters per second. And we get H max, of course, is equal to, notice the negatives cancel out. So I'm going to do 30 squared divided by parentheses 2 times 9.8, close parentheses. And lo and behold, I get 45.9184, so on and so forth. So we see that we get exactly the same expression we got before, exactly the same number we got before. So we can box that off and say that's H max. And we've confirmed it 2 ways now. So everybody sees how we actually had 3 different ways of doing that. 2 of them turned out to be identical. And then the third one was entirely different, but gave us the same answer. Does that make sense to everyone? Anybody have any questions on that? It looks like everybody has, but I'll just remind everybody, please chat me your first and last name so I'll have you for roll. We've gotten T1/2 and we've gotten H max now. So I'll go ahead and write these on the figure. This is 45.918. And that's meters, and the 1 and the 8 are not significant, so I underline them. So maybe we try now to get, let's get T hang time. Okay. Anybody have any ideas how to get T hang time? Use symmetry, use your understanding of motion. Tell me something I can do to find out what T hang time is.
Since halfway up is 3 seconds, would you be able to double it to get the other?
Excellent. Yes. That's just using the symmetry of the problem. If it, can anybody think of a time when that wouldn't work?
If it's a non-symmetrical motion?
Can you give me a specific example when it would be non-symmetrical? You're right. You're right on the money, but anybody else? You did
Air
the whole.
resistance.
Go ahead.
If you were just starting from like the halfway point, like something was just instead of going up and coming down, it just like went down
All right,
or
like
forward.
shooting off a horizontal
Yeah,
cliff or something like that, and you shoot it horizontally at first.
yeah.
Yeah, that. Or basically, anytime the landing and the takeoff are at different heights, it's not symmetric,
Oh, yeah.
right? Because to the left of the peak, it would only go a certain distance, but to the right of the peak, it'd go a different distance. That's why it's not symmetric, so we can't use that way. But yeah, you're absolutely right. So I'll say by symmetry, T hang time is equal to 2 times T 1/2, and that works. Okay. And in fact, you would say that T hang time would equal 3.0612 times 2 is going to give me 6.1224 with exactly as many extra digits as the previous one had, and that would be time. So I'm going to circle that as if it's a right answer. Now, can someone tell me another way to find T hang time? Do you know anything about, for instance, the acceleration at T hang time, or the velocity at T hang time, or the height at T hang time?
Would they both velocity and height be equal to 0?
Uh, that the velocity part's not quite right, but a lot of people always think that when we first start studying projectile motion and stuff like that. When we say hit ground, we mean just the instant before it hits ground. So the velocity wouldn't be 0 there, but that's the mistake that everybody makes. So don't feel bad about that. But you're exactly right. The height would be 0, right? So setting y equal to 0 is another way. So we're going to do that now and see if we get the right answer again. So now we're going to say THT when y equals 0. And this gives us, for instance, I'm going to say 0 is equal to, now I'm going back to equation 1, that's negative, I'm evidently going to randomly erase things because that's what my program does. Negative 4.90 meters per second every second times t squared plus 30.00 meters per second times t. All that's equal to 0. Now, one thing we can see from that is we can obviously factor out a t, and we're lucky in this case because if I had used a y0 not being 0, I'd have to use the Pythagorean, or excuse me, the quadratic formula, which is sometimes a mess and a pain in the butt. So that's not the best way, but it is a way that's completely fair and reasonable for me to expect students in this class to do. So just keep that in mind. Sometimes you might have to, but I'm going to factor out the t, and from that, I'm going to get negative 4.90 meters per second every second times t plus 30.0 meters per second parentheses. Now, remember, the whole reason in high school algebra 1 and algebra 2 or wherever you took it, the main thing is in that early algebra, we learned factoring, and a good reason that we learned factoring, other than just learning how to do mathematical things and learning skills and stuff like that, a good reason for it was that if you take a polynomial like 1/2 at squared plus v0t plus y0, and you have that as a polynomial, that's the sum of terms. That's what multi-term polynomial means. By factoring it, you convert a sum of terms into a product of factors. And when you have a product of factors equal to 0, then the only way that equation can be true is if one of those factors is exactly 0. So you just try each of the cases for each of the factors, and they each give you a separate answer. Okay. So with this in mind, what we can learn is that t equals 0 is one of them, and then I'll just say duh, right? Because clearly the thing was at a height of 0 when it first took off. Okay, so that's why that one is. But the other one gives us t hang time, which is equal to 30.0 meters per second divided by 4.90 meters per second every second. And if you do that division, you do 30 divided by 9.80, and you get, oops, wait a second. Oh, I divided by, yeah, 30 divided by 4.9, not 9.8, dumbhead. You get, in fact, 6.1224 seconds, which equals t hang time, which is exactly the same result we got before. Okay. So I'm now going to say 6.1224 seconds is t hang time. Anybody have any questions on that?
And this is the method we use if it's not symmetrical.
If it's not symmetrical, you could use this. Yeah, absolutely.
Okay.
Good point. I'm glad you pointed that out. Now that we have that, can anybody think of how we're going to find R, the range? I used R, by the way, because that's called range. But you could just call it, X max or something if you wanted to. So anybody have any ideas, either using using t hang time or not?
So we
Integration.
just use, sorry.
Oh, go ahead. Joseph, what were you gonna say?
I said integration.
Integration. We could, in principle. I'm thinking, hold on. No, I don't think that's going to help us, not in a clean way anyways. What do we know about anything at R? Do we know, for instance, how much time has passed? Okay. Do we know how fast the ball is actually going in the left-right direction?
Do we just use one of the kinematic equations with distance and then just isolate that?
Yeah, so you could use, for instance, equation 2, and we already got the hang time. So yeah, that's it. And that's what I was shooting for, seeing if y'all come up with that one. So for R, what I'm going to do is use equation 2 and say that R is equal to 40.0 meters per second times 6.1224 seconds. And when we do that, we'll say 40 times 6.1224, and that gives us 244.89. So 244.89 meters is equal to R, and that's another answer. Oops, don't know what happened there. Okay. Okay. Now I also should mention I multiplied 3 sig figs times 3 sig figs, so the 8 and the 9 are not really sig figs, it's just 244. So I'm going to say R is equal to 244.9 meters. Okay, so that's the range. Now, just to let you know, what I thought someone might have come up with is the fact that by symmetry, if you look at this, we have 3.0612 seconds from the time it took off with a vertical velocity of 30 meters per second until it gets to a vertical velocity of 0. And then you have 3.0612 seconds from the time it has 0 velocity in the y direction till the time it has whatever the final velocity in the y direction is. So can anybody guess what that final velocity in the y direction would be?
Would it just be gravity since it's on the way down?
Well, it is due to gravity, but we know exactly what gravity did in the first 3.061 seconds. So do we know what gravity would do in the next 3.061 seconds? These are tough questions. It's not, don't feel bad if you don't come up with them. I just thought you might think about it. Remember, I told you guys that the acceleration should be read as 9.8 meters per second every second. So when you allow the velocity or when you allow the projectile 3.0612 seconds, then in the first second, the velocity is going to decrease by 9.80. In the second second, it's going to decrease by another 9.80. In the third second, it's going to decrease by another 9.80. And then in the remaining 0.0612, it's going to decrease by another amount. You know that that remaining amount is enough to take it down to 0. So it's changing from 30 meters per second upward to 0 in 3.061 seconds. What do you think it's going to change from in the second half where it starts off at 0? What do you think its final velocity would be?
The negative 30?
Exactly.
Yeah.
Yeah. So one of the ways you might have thought to solve for t hang time is you could have took the velocity equation, the one that I called equation 3, see Vy of t equals that, and set that equal to negative 30. So if you set that equal to negative 30, you'd get exactly the 6.12 seconds. That would give you that. And then you could plug that back into, like I said, equation 2, and that would give you the range. Does that make sense? So that's another way you can actually do it. You can actually use the symmetry of the problem to realize that if it went from positive 30 meters per second up to 0 in 3.061 seconds, and then it started at 3.061 seconds at 0, then it must reach negative 30 meters per second in that time. And therefore, you know exactly what the final velocity would be in the y direction. Does anybody know what the final velocity would be in the x direction?
40.
Exactly. Notice equation 4 applies. So equation 3 and equation 4 both apply. We could have thought of using t hang time to find that Vyt is actually equal to, at the end of the t hang time would be negative 30 meters per second. But we could also use the Vx of t to realize that it's never going to change in the x direction. So now that we've uncovered those symmetries, we can just finally write out that V final sub x is just going to be 40.0 meters per second. Someone just, oh, they must have fell out and came back in. Okay. And actually, I should have been writing that in black. So when I do V final, what I do is symmetry tells us that Vy, or let me say V0y equals 30.0 meters per second implies V final y is equal to negative 30.0 meters per second. And equation 4 suggests, oh, that doesn't look like 4, that looks like an H. Equation 4 suggests that V final x is equal to V0x, which equals 40.0 meters per second. So that's a way where we can figure out the final velocity without really doing any calculations, just by reasoning. But we can also do it another way. So let's go ahead and do that. Let's say alternatively, T hang time is equal to 6.1224 seconds. Okay. And then Vy of t, which was equation 3, gave us negative 9.80 meters per second every second times t, plus 30.0 meters per second, so that V final is equal to Vy of t hang time, and that's going to be negative 9.80 meters per second every second times 6.1224 seconds plus 30.0 meters per second, which ultimately gives me negative 30.00 meters per second. Then we could use equation 4, Vx of t is equal to 40.00 meters per second, implies Vx of t hang time is equal to Vx final, which equals 40.0 meters per second. So that's the calculations we could have done. I'm going to move this over a little bit because it looks like it looks like it could be confused as doing something else. So I'm going to put it a little further over here, so it won't look like it's part of that other one. So that is V final sub y. And we can box that off like that. Okay. So that's another way. Now that we have it, we could just write V final is equal to 40.0 meters per second I hat minus 30.0 meters per second j hat, which also can be written as 40.0 meters per second x hat minus 30.0 meters per second y hat. Forgot my hat over here. And here's another way that can actually save you a ton of time in writing. I can also just write this as 40.0 meters per second, comma, negative 30.0 meters per second. See, when we use less than or greater than symbols, then we're actually specifying a vector. So that's a nice quick way of writing vectors without having to write I hats and j hats and k hats. And just about everybody recognizes that. In the physics world, we definitely do. Math world, maybe not so much. Okay. But the rule is, in general, as we told you yesterday, if someone gives you vectors in magnitude and direction format, and you're supposed to give them a vector back, you should put it back in that magnitude and direction format. So I'm going to show you how to do that now. What we're going to do is we're going to draw V final sub x is equal to 40.0 meters per second with the underscore there. And then V final sub y is 30.0 meters per second there. Now, from this, we can immediately see that we've got another 3, 4, 5 triangle. That angle is phi. So you'd say phi is equal to the tangent inverse of, notice I'm not putting any signs in there. I don't want you using signs with your trig functions because that's only just a really nice way to make mistakes unless you're paying very, very close attention. But when you do this, you're going to get 36.87 degrees. Okay. And then V final is going to be given by the Pythagorean theorem, which is 30.00 meters per second squared plus 40. Oh, that did not work out well. Plus 40.00 meters per second squared. And that gives you 50.00 meters per second. So we'd finally say that VF is equal to 50.0 meters per second at, notice this phi is measured clockwise down from the positive x-axis. So I can just write that as negative 36.87 degrees. And we now have that answer. Okay. Now we don't have much time left because I really tried hard to explain this. So I'm going to do this other way kind of quickly. And I'm going to do it for a generic problem. So this is one where it has initial velocity V0 at an angle theta. So I'll draw my little coordinate system again. I'll say the initial velocity is V0 at an angle theta. That tells me that V0x is V0 cosine theta. And that tells me that V0y is V0 sine theta. Okay. Remember, it's not, cosine doesn't always go with X and sine doesn't always go with Y. Sometimes you're taking the angle between the vector and the Y axis. So all bets are off. So just be careful with that. So now I can say y of t is equal to negative 1/2 g. Notice I'm just using symbols. So if we went to another planet, I could use the g for that planet. So by not putting in 9.8, I'm allowing it to be free. So I could do it for Jupiter or Saturn or Mars or whatever. T squared plus, I'm going to put the t between the V0 and the cosine and the sine specifically because it's hard to tell if you put the t after if you're supposed to be taking the sine of theta or theta times t. So I just put it that way. And now I'm going to say x of t is going to equal V0 t cosine theta. So we've got all that now. So there's like our equation 1, for instance. And here's our equation 2, for instance. So I could, again, solve for all those quantities. Okay. So first off, I might want, let's say H max. I'm going to use that other way, which is V y squared equals V0 y squared plus 2 times a times y minus y0. But now I'm going to set it up for this particular problem. I'm going to say 0 squared is equal to V0 squared we're talking about the y component here, so it's sine squared theta minus 2g, and then the y is actually the h max. So h max is equal to v0 squared sine squared theta over 2g. So that's a general formula for h max. I could solve for t 1/2. And the way I do that is I'd say, I would say Vy equals 0, or I could say it more specifically. V sub y of t 1/2 is equal to 0. And I could say that v sub y of t is equal to dy dt. So I can now say that from this, I get negative gt plus v0 sine theta is equal to vy of t. And then I could even go a little further by taking another derivative and see that a sub y of t is just negative g. So that's some extra stuff we can use. So now I can do that, and I can say Vy of t would be equal to negative g t 1/2 plus v0 sine theta, and I'm saying all that equals 0. So that gives me t 1/2 is equal to, actually, let me start writing in blue again. I don't know why I even switched to red. So t 1/2 is going to be equal to v0 sine theta over g. So that's another general formula. I could say R occurs when y of t is equal to 0. So I say, for instance, 0 is equal to t times negative 1/2 gt plus v0 sine theta. And obviously this time would actually be t hang time. One of those will be. In fact, I'm going to go ahead and get rid of that one. So this gives us specifically that t equals 0, and I'll say again, duh. And it also says that t hang time is actually equal to 2v0 sine theta over g. Notice it is exactly twice as big as t 1/2. Now R is equal to x of t hang time. So R is going to be v0 times 2v0 sine theta over g times cosine theta. So R is actually equal to v0 squared 2 sine theta cosine theta over g. And of course, there's a trig identity for this guy right here. This is in fact the sine of 2 theta. So we get R is equal to v0 squared sine 2 theta over g. And this actually shows us the difference between, as I suggested in class, the difference between Shaquille O'Neal's free throw and LeBron James or Michael Jordan or, dang it, I forgot his name again. Dang it. I think he played at UCLA. It was either that or Maybe he played it. I can't remember. Anyways, guy did really well in the Olympics the other day playing basketball. Dang, I can't remember his name. Anyway, if you actually take a graph of sine 2 theta, instead of it going from 0 to 2 pi, it really only has to go to from 0 to pi. So the graph ends up looking like this. Okay. And in fact, this is at pi over 2, which is 90 degrees. And for projectile motion, we don't care about angles any bigger than 90 degrees, because if you throw it bigger than 90 degrees, then you're actually throwing it less than 90 degrees, but in the backwards direction. So what you notice is for a given sine function, you have two angles. You have a low trajectory and a high trajectory, unless you're trying to maximize your throw. So this tells us that if you want to maximize the distance of your throw, and we're ignoring air resistance and throwing from the same height as we are landing, then we want to throw it at pi over 4, which is 45 degrees. And if we're not trying to throw at our absolute maximum, then we have two choices for every trajectory: the crappy Shaquille O'Neal free throw, or, God, I see his face still. Anyways, or the LeBron James free throw. Anybody come up with a basketball player for me, Geesh? Not Allen Iverson. That was a long time ago. Anyways, okay, so we're actually done. This is basically it. I may solve a couple more projectile motion problems next time when we meet, but we've really had enough time to get all this done. I am going to put at least the homework part, maybe part 1 and part 2. I'm going to at least put one of them to be due not at Sunday at 11:59 p.m., but rather at Tuesday at 11:59 p.m. I might actually put both, because I want you to have enough time to ask questions. Remember, on Monday by 11:59 p.m. on Sunday, actually, you have a online test on chapters 1 and 2 that are due. So make sure you get that knocked out. You get up to 3 chances, and only your highest score counts. So please don't forget that. You guys are free to go. Make sure you chatted your first and last name in already, but go ahead and go, and I'll wait for the last person to leave in case anybody has any questions. I see Berenice is here. Berenice, you have a question?
Yes, sir. It's more of a not really a specific question. I just wanted to talk to you.
Okay, no problem. Is it something where we need private? Because I can stop recording. We can go into a virtual room if you want, so then nobody else here can hear the conversation.
I would prefer that.
Okay, yeah, hold on a second. Let me do this. I'm going to stop sharing for a second, and I am going to. Does anybody else have any questions before I get started with her?
Well, I'm from your TO2 class and I got questions.
Oh, okay. I didn't even notice you were there. Okay, hold on, Mark. I'll get. Is that you, Mark?
Yep.
Okay. Let me go ahead and get that. And Diego, are you here for this class or for something else? I think you're in this class, if I remember correctly. Okay, so I got that. I'm going to do breakout room. That's what I'm trying to do here. So I mean, breakout room. Nope, not that. Not that. Okay. Not that. That didn't work either. I tell you what. I'm having some difficulty finding what I need right now. I just sent you a number. Can you call me on that and I'll talk to you there? I'll still have
Yes,
the
sir. I
computer.
will do that.
Okay, go ahead and do that. And I'm gonna just mute this right now. Everybody, I'm still gonna be here, Mark, so I still have time to answer your questions and stuff. Just it'll take a second for me to answer her question, and then I'll get right back with you. Okay, bud?
All right, I just stay in this room then.
Okay, thank you, sir.